Deep under the border of France and Switzerland, a machine 17 miles around smashes particles together at almost the speed of light. In December, it spat out a result that bent the rulebook scientists had trusted for 50 years. We're going inside the strangest signals ever caught at CERN. A particle that fell apart the wrong way. Matter that beat its evil twin. Antimatter. Trapped and then dropped, just to watch which way it falls. If this blows your mind, hit like and subscribe. Helmets on. We're going down. Picture a circle so big it crosses an international border, and it sits about 100 feet beneath your shoes. That circle is real. It runs under farms, under villages, under the edge of the Alps, looping out of Switzerland, into France, and back again. End to end, the ring stretches about 17 miles. If you tried to walk a lap, it would eat up most of your day. The people who work there actually ride bikes through the tunnel to get from one section to the next. This is CERN, the largest science machine humans have ever built. Its full name is a mouthful, so almost everyone just says CERN. The heart of it is called the Large Hadron Collider, a name that sounds scary and turns out to be simple once you crack it open. Large, because it is enormous. Collider, because its whole job is to crash things together. What does it crash? Tiny pieces of stuff called protons. A proton is one of the bits inside an atom, and an atom is already so small that millions of them could sit on the period at the end of this sentence. So we are talking about smashing the smallest things you can imagine, on purpose, billions of times a second. Here is the part that sounds fake. Inside the tunnel, those protons race around the loop at almost the speed of light. That is around 670 million miles an hour. At that speed, a single proton laps the full 17-mile ring more than 11,000 times every second. Light from your phone screen could barely keep up. To steer something moving that fast, you need force, and a lot of it. CERN uses giant magnets, thousands of them, lined up along the whole tunnel. These magnets are colder than outer space. Engineers chill them down near the lowest temperature anything can reach, colder than the dark between the stars, so they can carry massive power without melting. Then the machine does something wild. It takes two streams of protons flying in opposite directions and aims them straight into each other, head on. The crash is so violent that for a flicker of a moment, in that tiny spot, the temperature climbs to more than 100,000 times hotter than the center of the sundae. For that flash, scientists create a little echo of the newborn universe, the way everything looked right after the Big Bang. Out of the wreck of each crash, strange new particles spray outward. Most of them vanish in less time than it takes light to cross a single atom. Catching them is the entire point. So why build a 17-mile monster, freeze it colder than space, and fire lightning-fast particles into each other? Why spend years and billions of dollars to watch tiny things shatter? Because every collision leaves clues in the wreckage. Clues about what everything is made of. Clues about where we came from. And lately, that wreckage has started whispering something the smartest people on Earth did not expect, and still cannot explain. To understand why that whisper is so frightening, you first need to meet the rulebook it might be breaking. The collider is also a time machine, and it only travels in one direction, backward. Here is how that works. When you look at a star, you see old light. Some of those stars sit so far away that their glow took thousands of years to reach your eyes. So you are staring at the past. CERN does something similar, except instead of waiting for ancient light, it builds the past on purpose. Rewind the universe far enough and everything changes. Today the cosmos is cold and spread thin, full of planets and stars and empty space. But run the clock backward, all the way to the start, and it all squeezes together, hotter, denser, until you reach a moment less than 1 second after the Big Bang. At that moment, the universe was one glowing fog, thicker and hotter than anything around you now. Atoms had not formed. Water, air, and solid ground were still millions of years away. Scientists call this fog a quark-gluon plasma. Think of it as the soup that everything else was later cooked from. Quarks are the tiny building blocks locked inside protons. Gluons are the force that normally holds those quarks together so tightly they can never break free. But in that first hot instant, the soup ran so wild that the quarks roamed loose, like sparks flying free before they cool and stick. CERN can brew a droplet of that soup. When the collider slams heavy particles together hard enough, it melts them for a flicker into the same free-flowing plasma the universe wore as a baby. The droplet is unbelievably small and gone almost instantly. Yet for that flash, a corner of Switzerland holds a piece of the morning of time. Studying that soup shows scientists how the early universe acted as it cooled. They watch how the quarks slow down. They measure how the fog flows. And weirdly, it flows like a liquid, the smoothest liquid ever measured, with almost no friction at all. A drop of honey is sticky and slow. This early universe soup pours more perfectly than water, more perfectly than anything we know. Every measurement is a page pulled back from the universe's lost first chapter, and each page raises the same haunting question. If we can rebuild the beginning, can we finally explain how the beginning built us? Because something went right in those first moments. Something turned a featureless hot fog into stars, planets, oceans, and you. The rules that pulled off that magic trick are stamped into every crash CERN makes. Most of those rules already sit inside one famous rulebook, a list so successful it has survived every challenge thrown at it for 50 years. Scientists lean on it the way you lean on gravity, trusting it will always hold, but a rulebook is only as strong as its next test. And the collider was built to test this one harder than anything before. So before we reach the signal that has everyone rattled, you need to meet the rulebook itself and understand why breaking it would shake the ground under all of science. Every game you have ever played runs on rules, and the universe is no different. Physicists wrote those rules into one list, and they gave it a boring name. The Standard Model. Boring name, incredible power. This single list explains what everything around you is made of, using a small set of building blocks and a few forces that push and pull them around. Think of it as a periodic table for the truly tiny. It names every basic particle we know, the quarks that build protons, the electrons that buzz around atoms, the particles of light, a handful of rare, heavy cousins that flash in and out of existence. Add them all up, and the entire menu of stuff fits on a single chart, smaller than a poster on your wall. What makes the Standard Model legendary is not just what it lists. It is how often it has been right. Again and again, the math predicted particles nobody had ever seen. Then, years later, sometimes decades later, scientists built a machine, ran the experiment, and there the particles sat, exactly where the rulebook promised. It called the W particle and the Z particle before anyone found them. Found. It called the top quark. Found. And in 2012, it nailed its most famous prediction of all, a particle hunted for almost 50 years. We will reach that one soon, because it explains something strange about you. For half a century, this rulebook has passed every test thrown at it, every collision, every measurement, every trap scientists set to catch it slipping. Each time, the Standard Model shrugged and held. That track record makes it the most successful idea in the history of science. Nothing else comes close. So, you might think physicists adore it. In a way, they do. But here is the twist that keeps them awake at night. They already know it is incomplete. The Standard Model, as flawless as it looks, leaves huge gaps. It says nothing about gravity, the force gluing you to the floor right now. It has no answer for the invisible stuff that makes up most of the universe. And it cannot explain why you, your friends, and your whole planet are even here instead of nothing at all. So scientists are stuck with a strange feeling. They hold the most accurate rulebook ever written, and they are certain pages are missing. Somewhere out there, buried in the math, there must be more. New particles, new forces, a deeper layer nobody has cracked. That is the real reason CERN exists. The collider was built to push the rulebook until it finally bends, to find the first crack, the first measurement that comes back wrong, the first clue pointing toward those missing pages. For years, the machine pushed and pushed, and the rulebook held firm. Test after test came back perfect, almost annoyingly perfect. Scientists started to wonder if they would ever see it crack at all. Then, late in 2025, deep inside a pile of data, one rare event came back looking wrong, badly wrong. Wrong in a way that made experienced scientists lean closer to their screens. To understand what they saw, you first have to understand how a particle dies. The crashes happen in a flash, so CERN wraps them inside the most powerful cameras on Earth. Forget the camera in your phone. These are machines the size of buildings, packed tight around the exact spots where the protons collide. Each one is a detector. Its only job is to catch the spray of particles blasting out of a crash and figure out what just happened billions of times every second. The biggest detector is called Atlas. It stands taller than a 6-story building and weighs about as much as the Eiffel Tower. Picture a camera so heavy it could flatten a house, built to photograph things far too small to ever see. Another giant, called CMS, weighs even more, heavier than 30 fully loaded jumbo jets stacked together. These are monsters built to study the tiniest things in existence. So, how do you photograph something smaller than an atom? You do not snap a picture of the particle itself. You track the trail it leaves behind, like a detective following footprints in fresh snow. As each particle rips outward from a crash, it punches through layer after layer of the detector. Every layer records a tiny ping. Stitch all those pings together, and you can trace the exact path the particle took, how fast it moved, and which way it curved. That curve matters most of all. The whole detector sits inside a powerful magnet, and a magnet bends the path of a moving particle. Heavy particles bend a little, light ones bend a lot. By measuring the curve, scientists work out what kind of particle flew by, even though it lived for less time than you could ever blink. Now, picture the scale of the problem. Inside the collider, crashes come so fast that the detectors face around 40 million snapshots every second. 40 million. If you tried to save them all, you would jam every hard drive on the planet in minutes. So lightning-fast computers make a brutal choice in a sliver of a heartbeat. They dump almost everything and keep only the rare crashes that look interesting. This is where one special detector steps into the story. It is called LHCb, and it is the hero of the mystery we are chasing. While the giant detectors hunt for brand new particles, LHCb watches for something sneakier. It studies how certain particles fall apart, searching for tiny gaps between how the rulebook says they should behave and how they actually do. Most of the time, the answer is boring. The particles behave. The rulebook wins. Scientists log the result and move on. But LHCb is patient. It has watched hundreds of billions of these tiny breakups, one at a time, year after year, slowly stacking a mountain of data. And buried in that mountain, the team went hunting for one specific kind of breakup, so rare it barely ever happens. That breakup carries a strange nickname. Scientists call it the penguin. Before you can understand why a penguin shook the foundations of physics, you need to understand what really happens when a particle falls apart. Some particles are born already dying, and they fall apart almost the instant they appear. That falling apart has a name. Scientists call it decay. It sounds gloomy, but it is one of the most important things in all of physics, and a little of it is happening inside your body right now. Here is the basic idea. The universe is packed with particles, and some are stable. An electron, for example, can last forever, but many particles are heavy and restless. They carry too much energy to sit still, so they shatter into lighter, calmer pieces almost as soon as they form. A heavy particle decays into smaller ones, and those might decay again like a tower of blocks collapsing into a scattered pile. Think of a snowflake landing on warm skin. For a heartbeat, it holds its perfect shape, then it melts into something simpler. Many particles live far shorter lives than that. Some last less than a trillionth of a second before they transform. You could never watch it happen. You can only study the pieces left behind. And those pieces are everything. When a particle decays, the rulebook controls exactly how it can fall apart, what it can turn into, and how often. A certain heavy particle might break into one set of lighter particles most of the time, and a different set only once in a great while. Scientists have measured these patterns for decades, and they line up with the standard model with stunning precision. This is why decays are such a powerful tool. They work like a fingerprint. If you watch enough particles fall apart and count how often each pattern shows up, you can test whether the universe is truly obeying its own rules. When the counts match the rulebook, all is calm. When the counts come back wrong, alarms start ringing. CERN is, in a way, a giant decay-watching factory. The collisions create swarms of heavy, unstable particles, and the detectors sit there recording how each one comes apart. Most decays are common and well understood. Scientists have seen them millions of times, expected, filed away. But the rarest decays are the real treasure. Some breakups happen only once in a million tries, or even less. Those rare events are exactly where hidden surprises like to lurk. A strange new particle, one too heavy for the collider to ever create directly, could still reach in like an invisible hand and nudge a rare decay slightly off course. That is the dream. Find a decay so rare and so delicate that an unknown force, hiding just out of reach, leaves its fingerprints all over it. Catch the universe bending its own rules in a spot nobody was watching. For years, the team running LHCb chased one decay like this. A breakup so rare, it shows up about once in every million tries. They watched and waited and counted, gathering hundreds of billions of crashes, hunting for just a sprinkle of these strange events. When they finally gathered enough and held the result up against the rulebook, the numbers refused to line up. The decay was behaving in a way the standard model could not explain, and the name of that rule-bending breakup brings us right back to a very unexpected animal. Physicists named one of the strangest events in the universe after a cartoon bird, and the reason is gloriously silly. To get there, you first need to meet the star of our mystery, a particle called the B meson. When the collider smashes protons together, the wreckage sometimes forms this heavy little blob. Tucked inside, it is a rare, hefty building block that scientists call the beauty quark. That quark makes the B meson special, and it also makes it doomed. The B meson is unstable, so it falls apart almost the moment it is born. Most of the time, it breaks apart in plain, ordinary ways. But once in a great while, around one time in a million, it does something far rarer. It shatters into 4 smaller particles all at once. 2 of them are called a kaon and a pion, lightweight bits that show up all over particle physics. The other 2 are muons, which you can picture as electrons that hit the gym and bulked up, heavier and more powerful than the normal kind. So why on earth is this called a penguin? Back in the 1970s, a young physicist lost a friendly bet over a dart game. The deal was that he had to slip the word penguin into his next science paper. He was studying these exact decays, and scientists love to draw decays as little stick diagrams that map out what turns into what. When he looked at the diagram for this kind of breakup, with its loop and its dangling lines, he decided it sort of looked like a penguin standing up. The name was a joke. It stuck anyway. Now, serious scientists at CERN say penguin decay with completely straight faces. Behind the goofy name sits a deadly serious idea. This decay is one of the best traps in all of physics. Here is why. It is so rare and so delicate that any tiny outside influence would show up loud and clear. Imagine a perfectly still pond. Drop in a single pebble, and you spot every ripple. A common Messy decay is like a stormy sea, where a pebble vanishes without a trace. But a rare penguin decay is that still pond. If some unknown particle is hiding out in the dark, too heavy for the collider to ever create directly, it could still reach in like an invisible hand and disturb this fragile breakup. And we would see the ripples. That is the whole strategy. You cannot always catch the monster itself, but you can watch a still pond and look for the splash it leaves behind. So the team running LHCb went hunting. They sifted through an almost unimaginable pile of data, around 650 billion B mesons, recorded over several years of crashes. Out of that mountain, they pulled the tiny sprinkle of penguin decays, the rarest of the rare, and lined them all up to study. Then they did something clever. They did not just count how often the penguin happened, they measured the exact way it fell apart, the angles, the directions the muons flew, the fine details the rulebook claims to predict down to the last decimal. And when they compared their measurement to what the standard model demanded, the numbers refused to match. The penguin was misbehaving. Something about the way it fell apart was bending away from the rules. What exactly came back wrong? The answer is one strange number that has haunted physics for over a decade. The penguin happened almost exactly as often as the rulebook predicted. So at first, nothing looked wrong. The trouble was hiding in the angles. Think about it like this. When the B meson shatters into those four pieces, they do not just fly off any old way. They spray outward in a pattern, like sparks bursting from a firework. The rulebook does more than say how often this happens. It claims to know the shape of the spray, the exact angles the muons should take as they race away from the wreck. Scientists built a special measuring stick just for this. It is a kind of angle score, designed by very clever people to be as clean and trustworthy as possible. They worked hard to strip out the fuzzy, hard-to-calculate parts, so that whatever was left would be a fair, honest test of the rules. The standard model predicts one clear value for this angle score. Nature should obey. Nature did not obey. The collider kept measuring an angle score that sat off to the side of the prediction, not wildly off, just stubbornly, consistently off in the same direction, again and again. Here is the part that gives this story its weight. This wobble is old. It first showed its face back in 2013, when scientists noticed the angle score drifting away from the rulebook. Back then, it was faint, the kind of thing that could easily be a fluke. They figured more data would wash it away, the way a blurry shape sharpens into nothing when you step closer. So they gathered more data. The wobble stayed. In 2016, with a bigger pile of crashes, they checked again. Still there, same direction, roughly the same size. A signal that refuses to die is either a mistake nobody can find, or it is real. Then came December of 2025. The team rolled out their most powerful study yet, built from the largest and most carefully cleaned dataset they had ever assembled. Years of work, hundreds of billions of decays, the most precise look at this penguin in history. The wobble did not just survive, it grew. When they combined everything, the gap between the measurement and the rulebook reached a level scientists call 4 sigma. Picture it as a tug of war between two numbers, the prediction on one side, the measurement on the other, and the rope had stretched to its most strained point ever. The reaction was immediate. Physicists who had watched this number flicker for over a decade leaned in close. For years, they had a quiet hope and a quieter fear. The hope was that the rulebook was finally cracking, revealing those missing pages everyone knows are out there. The fear was that it was all a trick of bad luck or sloppy math. 4 sigma pushed the hope ahead of the fear, barely, carefully, but ahead. Now, you have probably heard scientists throw around words like sigma without ever explaining them. It sounds like jargon, and most videos just skip past it. But this single word is the difference between a headline and a yawn, between a real discovery and a ghost that fools everyone. So before we go any further, you need to understand exactly what 4 sigma means, and why that number alone made experienced scientists hold their breath. Sigma is just a fancy word for one simple question. How shocked should you be? Let me show you with a coin. Flip a coin 10 times. Getting 6 or 7 heads would not surprise you at all. That is normal randomness, the everyday wobble of luck. But flip a coin 10 times and land 10 heads in a row, and your eyebrows go up. Flip it 100 times and get 100 heads, and you stop believing it is a fair coin at all. Something is going on. Sigma measures exactly that feeling, but with real numbers instead of gut instinct. It tells you how far a result sits from boring, ordinary luck. 1 sigma is nothing. Results land that far from the prediction all the time, just from random noise. Picture it like missing a dartboard's center by an inch. Happens constantly. 2 sigma is a little interesting, the kind of thing that makes you look twice, but not panic. 3 sigma starts to feel strange, the dart landing in the same odd corner several throws in a row. 4 sigma, the level our penguin reached, is a different beast. At 4 sigma, the odds that pure random luck created the result drop to about 1 in 16,000. Sit with that for a second. If this wobble were just bad luck, you would have to repeat the whole experiment around 16,000 times before chance alone coughed up a fluke this big. Here is a way to feel that number. Imagine a stadium packed with 16,000 people, about the size of a big arena crowd at a concert. Now, imagine that out of every single person in that roaring crowd, only one holds a golden ticket. You reach in blindfolded, pull one person at random, and somehow grab the exact ticket holder. That is how unlikely it is for this penguin wobble to be a simple accident of chance. So when scientists saw 4 sigma, their instincts screamed that something real was happening. The measurement was not landing near the rulebook and drifting off by accident. It was parked far away, stubbornly, with luck almost ruled out as the cause. You might think that settles it. 1 in 16,000 sounds like a slam dunk. In almost any other field, it would be. If a new medicine worked that reliably, doctors would celebrate. If a weather forecast were that confident, you would trust it without blinking. But particle physics plays by the harshest rules in all of science. Crueler than medicine. Crueler than almost anything. In this world, 1 in 16,000 is not a discovery. It is not even close. It is officially still a maybe, a tantalizing hint that scientists are forbidden from celebrating out loud. That sounds insane. Why would anyone throw away odds that good? Why refuse to call something real when luck has been beaten down to 1 chance in 16,000? The answer reveals the most paranoid, most disciplined corner of all of science. Physicists have been burned before, badly, by signals that looked just this convincing and then vanished into thin air. To understand why they hold the line so stubbornly, you need to learn the brutal gold standard they refuse to break. To officially announce a discovery, physicists demand a level of proof so extreme it borders on paranoid. The magic number is 5 sigma, just 1 step up from where our penguin sits, yet that single step is a giant leap. At 5 sigma, the odds of the result being a random fluke crash down to less than 1 in a million, closer to 1 chance in 2 million. Only when a signal climbs that high are scientists allowed to stand up and say the word discovery without getting laughed out of the room. So, why such a savage standard? Why is 1 in 16,000 treated like a rumor while 1 in 2 million is treated like truth? The answer hides in a sneaky problem called the look everywhere trap. Picture this. Scientists at CERN are not running one experiment. They are running thousands of measurements, checking countless particles, examining endless ways things can decay, year after year. Now, remember that a 4 sigma fluke can pop up by pure chance roughly 1 time in 16,000. When you are measuring tens of thousands of things, a 1 in 16,000 coincidence stops being rare. It becomes almost guaranteed to show up somewhere, eventually, by accident alone. Think of it like a giant lottery. Your personal odds of winning are tiny, but sell enough tickets to enough people and somebody is going to win for sure. That winner did nothing special. They just got lucky in a sea of millions. A 4 sigma blip can be exactly that kind of accidental winner, a coincidence that looks meaningful only because so many numbers were checked. History has burned physicists with this over and over. Signals that looked rock solid melted away the moment more data arrived. Real, careful scientists got excited, wrote papers, gave talks, and then watched their beautiful discovery evaporate. It is humiliating. It is also how science protects itself from fooling everyone, including its own true believers. So 5 sigma became the wall. Cross it, and the odds of being tricked by luck are so small that the result almost has to be real. Stay below it, and no matter how thrilling the hint, it stays filed under maybe. This is why, even now, the rulebook technically still stands. The penguin wobble is loud. It is stubborn. It has survived for over a decade and only grown stronger. But it has not yet smashed through that 5 sigma wall, so the official line stays cautious. The standard model has not fallen. It has only started to tremble. You can feel the tension this creates. Scientists are staring at a result that beats odds of 1 in 16,000, a result that has refused to die for years, and they still have to bite their tongues and say maybe. The excitement is real, so is the discipline holding it back. A 4 sigma hint from a single machine could, in theory, still be some hidden flaw nobody has spotted, a scratched part, a sneaky bug in the software, one lab fooling itself. So there was one question that mattered more than any other. Was anyone else seeing this? Could a completely separate machine, built by a rival team, with different parts and different methods, look at the same penguin and find the same crack? The answer turned a quiet hint into something far harder to ignore. If one machine sees a ghost, you can blame the machine. If 2 machines built by rival teams see the same ghost, you have to start believing in the ghost. Remember that the collider does not have just one detector watching its crashes. The team chasing the penguin used LHCb, the specialist built to study these delicate breakups. But sitting elsewhere around the same giant ring is another monster detector called CMS. This is the heavyweight, the one that weighs more than 30 loaded jumbo jets stacked together. Different shape, different parts, different software. Run by a completely separate army of scientists who would love nothing more than to prove their rivals wrong. That rivalry is the secret weapon of science. When 2 competing teams use 2 different machines and reach the same answer, it becomes very, very hard to wave the result away as a simple mistake. A flaw in one detector almost never shows up in the exact same way in a totally different one. So scientists waited to see what CMS would say about this penguin. It found the same thing. When the CMS team measured the same kind of decay, their result drifted away from the rulebook in the same direction by a similar amount. Their measurement was not as sharp as the LHCb one. Picture 2 people describing the same shadowy figure across a field. One has binoculars, the other has bare eyes. The one with binoculars sees more detail, but both point at the same spot and say, yes, there is something there. 2 machines, 2 teams, 2 completely separate ways of crunching the data, both pointing at the same gap, in the same place, in the same direction. This is the moment the story changed. A lone 4 sigma hint from a single detector is the kind of thing seasoned physicists have learned to distrust, because they have been fooled by exactly that before. But a wobble that shows up in 2 independent machines is a different animal. It is the difference between 1 witness and 2, between a single, blurry photo and 2 photos, snapped from across the room. The combined picture is now the strongest case in years that something genuinely new might be lurking at the deepest level of reality. Not proven, not a discovery. The 5 sigma wall still stands untouched. But for the first time in a long time, the rulebook that ruled physics for 50 years looks like it might actually be wrong, and 2 separate giants are both whispering the same warning. You can imagine the buzz. Conferences lit up, late-night arguments, Scientists who spent their whole careers trusting the standard model suddenly forced to ask whether the missing pages were finally peeking through. And yet, even with two machines agreeing, the smartest people in the room refuse to fully celebrate. They cannot, because there is one loophole left, one messy, frustrating possibility that could explain this entire wobble the boring way with no new physics at all. It comes down to a piece of math so fiendishly hard that nobody on Earth can calculate it cleanly. If that messy math is hiding a bigger effect than anyone thinks, the whole mystery could collapse back into the rulebook, leaving nothing strange behind. And in keeping with the grand tradition of this story, that troublemaker has its own ridiculous nickname. The whole mystery might collapse because of a tiny troublemaker that scientists nicknamed the Charming Penguin. The name sounds adorable, and the problem behind it is a nightmare. To understand it, you need to remember why scientists trust their angle score in the first place. They claim the rulebook predicts that number with razor sharpness. So when the measurement comes back off, it looks like the rulebook is wrong. But here is the catch. To know the exact prediction, you have to do some math. And one part of that math is so brutally hard that nobody on the planet can solve it cleanly. That hard part involves a particle ingredient called the charm quark. When the B meson falls apart, charm quarks can briefly flicker into the process, almost like extra guests sneaking into a photo at the last second. These flickering charm quarks blur the prediction. They add a smudge to the math that scientists cannot fully scrub away. Because the smudge involves a charm quark sneaking into the penguin decay, physicists smiled and called it the Charming Penguin. Now you can see the danger. If those sneaky charm quarks have a bigger effect than scientists think, they could push the angle score off course all by themselves. No new particles, no missing pages, no revolution, just a known piece of the rulebook that nobody calculated well enough. The whole thrilling wobble could turn out to be ordinary physics wearing a disguise. So how big is the Charming Penguin's effect? That is the multi-million-dollar question, and the honest answer is that nobody is completely sure. The best calculations scientists can manage suggest the charm quark smudge is too small to explain the entire wobble. The numbers come out short. That points towards something genuinely new, but there is a humbling problem. The math is so tangled that scientists cannot fully trust their own answer. Picture trying to measure the width of a single human hair using a ruler from your pencil case. The ruler only marks down to a 1/4 inch. No matter how carefully you squint, you simply cannot read a measurement that fine. The tool is too clumsy for the job. The charm quark calculation is a lot like that. The question is delicate, and the math tools are just not sharp enough to give a clean, final answer. This is the loophole that keeps the rulebook alive. As long as scientists cannot rule out a fat, charming penguin, they cannot be certain the wobble is new physics. The boring explanation refuses to fully die, so the situation sits balanced on a knife edge. On one side, two separate machines see the same crack, and the best math says the charm quark cannot fill it. On that reading, the universe is hinting at something never seen before. On the other side, a fiendish calculation nobody can finish might be hiding a bigger smudge than anyone expects, ready to swallow the whole mystery and leave the rulebook standing. This is exactly why scientists refuse to celebrate. They have been here before. They have stared at a beautiful, convincing signal that beat huge odds, written excited papers about it, and then watched it crumble into dust. There is one story that haunts every physicist who looks at this penguin, a signal that looked even stronger than this one, a discovery that hundreds of scientists rushed to explain, and then, almost overnight, it vanished, as if it had never existed at all. That ghost is the cautionary tale you need to hear next. A few years ago, the same collider showed scientists a bump in the data so exciting that hundreds of them dropped everything to chase it. Then it disappeared, and the lesson still stings. It happened back around 2015. Two of CERN's giant detectors, working separately, Both spotted something odd in their crashes. When certain collisions produced pairs of light particles, an unusual number of those pairs carried roughly the same hefty weight, a value near 750 on the scale physicists use. A little pile-up of events, sitting exactly where the rulebook predicted nothing special at all. A bump like that is the dream. It is the classic fingerprint of a brand new particle. Something heavy and unknown, briefly appearing and then falling apart into that telltale pair. And the thrilling part was that two different detectors, run by rival teams, both saw the same bump in the same spot. That is the very thing that makes a signal hard to ignore. The same thing happening with our penguin today. The physics world caught fire. Scientists looked at the bump, did the quick math, and realized it sat at a strength of around 3 to 4 sigma. Strong enough to make hearts race, strong enough to feel real, and so the gold rush began. In just a few months, scientists wrote roughly 500 papers trying to explain the bump. 500. Researchers around the globe stayed up late, spinning out theories about what this new particle might be, what secrets it could unlock, how it might crack the rulebook wide open. Careers pivoted, reputations leaned in. Everyone wanted to be first to name the discovery of the century. Then more data arrived. The collider kept running and kept collecting crashes. Scientists fed the fresh data into the same analysis, eyes glued to that magic spot near 750, waiting for the bump to grow taller and cross the 5 sigma wall into glory. The bump shrank, then it flattened, then it was gone, as if someone had quietly erased it. The whole thing had been a fluke. A random pile-up of ordinary events that happened to clump together and fool everyone. Exactly the kind of accident that statistics warns can sneak through when you check enough numbers. 500 papers, written about a particle that never existed. The bump was a ghost, and the ghost evaporated the moment the light got brighter. This was not the first time. Years earlier, another CERN machine saw a hint of a particle that climbed toward 4 sigma and then melted away with more data. A different lab once saw a signal that screamed even louder, and it too dissolved into nothing. Over and over, beautiful results have lured brilliant people in, only to vanish like a mirage on a hot road. That history is the cold water every physicist keeps nearby. It is why they refuse to pop the champagne over our penguin, no matter how stubborn the wobble looks, no matter how many machines agree. They have been burned. They remember the 750 ghost. They know luck can wear a very convincing mask. So the team studying the penguin holds the line. They say maybe. They say promising. They say the evidence is mounting. They will not say discovery, because they refuse to be fooled twice. And yet, if the penguin wobble is real, if it survives the next flood of data, it raises the most thrilling question in the story. What exactly is doing the tugging? What unseen thing could be reaching into a decay and bending the rules of reality? If the wobble is real, then something invisible is reaching into that decay and nudging it off course. And whatever that something is, the collider cannot see it directly. That sounds impossible. How do you detect a particle your machine is not powerful enough to create? The answer is one of the cleverest tricks in all of science, and it works a lot like a detective solving a crime nobody witnessed. Imagine a still room where a door slowly swings open on its own. You never see a hand, you never hear footsteps, but the door moved, so something pushed it. By studying exactly how it swung, how fast, how far, in which direction, you can work out a surprising amount about the invisible thing that did the pushing, even though it stayed completely out of sight. That is the whole idea behind the penguin. A rare decay should fall apart in a precise way. If a hidden particle exists, even one far too heavy for the collider to build, it can still flicker into the process for the tiniest instant and tilt the outcome. We never see the particle. We only see the tilt. The bent angle is the swinging door. This trick has cracked huge mysteries before. More than 100 years ago, scientists studied a strange kind of radioactivity, a way certain atoms quietly fall apart. They could measure it, but they had no idea what caused it. The particle truly responsible stayed hidden for around 80 years until a powerful enough machine finally created it and confirmed it was there all along. The clue came first. The proof came lifetimes later. So, what could be tugging our penguin? Scientists have a few suspects, and they are wild. One idea is a brand new force of nature. You already know about a handful of forces. Gravity holds you to the ground. Another force lights up magnets and electricity. There may be a fifth force out there, faint and shy, one we have simply never noticed because it barely whispers. A force like that could lean on the penguin just enough to bend it. Another suspect is a strange new particle that does something no known particle can do. It would act like a bridge, linking two families of particles that the rulebook keeps strictly apart. Picture a secret hallway connecting two parts of a building that were supposedly sealed off from each other. If a particle like that exists, it could quietly carry influence across that hidden hallway and reshape the decay. Here is the staggering part. If either suspect is real, it would be the first crack in the most successful rulebook in history. The first hard proof that the standard model is missing pages. The first time in 50 years that physics caught a glimpse of something genuinely beyond the map. Whole new chapters of science would burst open, the kind of moment that rewrites textbooks and reshapes how we understand everything that exists. That is why the stakes feel almost unreal. A bent angle in a 1 in a million decay could be the loose thread that unravels our entire picture of reality. But the penguin is only one of CERN's mysteries. And to feel the full weight of what this machine has found, you have to step back to its most famous victory. A particle hunted for nearly 50 years. A particle that explains something strange about your own body right now. There is a particle that decides how much you weigh, and scientists chased it for almost 50 years before they finally caught it. It is called the Higgs, and to understand why it matters, you have to ask a question that sounds almost too simple. Why does anything have weight at all? Why is a bowling ball heavy and a feather light? Why does a planet pull harder than a pebble? The deep answer is stranger than you would ever guess. Back in the 1960s, a quiet scientist named Peter Higgs proposed a bizarre idea. He suggested that all of space, every inch of it, is secretly filled with an invisible field. Not air, not light, something far weirder, woven into the emptiness itself. And as particles move through this hidden field, it drags on them. That drag is what we feel as mass. Picture walking across a room. Easy. Now picture wading across a swimming pool. The water clings to you, slows you down, makes every step heavy. The Higgs field works a little like that pool, except it fills the entire universe. Some particles barely feel it and slip through almost untouched, staying light. Others get gripped hard and turn heavy. The amount each particle interacts with the field is what sets its weight. This idea was beautiful, and for decades it was just an idea. To prove the field was real, scientists needed to find its matching particle, a ripple in that invisible pool. They called it the Higgs particle. The trouble was that it is heavy, shy, and falls apart almost instantly. Catching it would take a machine far more powerful than anything that existed. That machine became the Large Hadron Collider. Finding the Higgs was one of the main reasons it was built in the first place. For years, the giant detectors smashed protons together and sifted through the wreckage, hunting for the faint fingerprint of a particle that vanished the moment it formed. In 2012, they found it. The crowd at CERN erupted. Peter Higgs, by then an old man, sat in the audience and wiped away tears as scientists confirmed the particle he had dreamed up half a century earlier. It was one of the greatest victories in the history of science. The rulebook had made a daring promise, and the universe had kept it. Now here is why this touches you directly. Without the Higgs field, particles would have no weight. With no weight, they would all rocket around at the speed of light, never slowing down, never sticking together. Atoms could not form. Without atoms, there are no molecules, no water, no rock, no air, no cells, no you. The very fact that you are sitting here, made of solid stuff, exists because that invisible field grips the particles in your body and gives them weight. So the Higgs is not some far-off curiosity. It is the reason you have a body at all. The reason the universe is filled with things instead of just a blur of racing light. And finding it proved something powerful. When the rulebook makes a wild prediction, it tends to be right, which makes the penguin wobble even harder to dismiss. The same kind of physics that nailed the Higgs is now whispering that something is off. But the Higgs answers how you got a body. It does not answer a far deeper riddle. Why is there anything here to weigh in the first place? By every rule, scientists know you should not exist, nor should the stars, the planets, or a single speck of dust. The universe should be empty. This is one of the biggest unsolved mysteries in all of science, and it begins at the very moment the universe was born. Rewind to the Big Bang, the colossal burst of energy that started everything. In that first searing instant, the universe was nothing but pure energy. And one of the firmest rules in physics says that when energy turns into matter, it never makes just one thing. It always makes a matched pair. Every time a particle of matter pops into being, a mirror version pops out beside it. Scientists call that mirror version antimatter. For every speck of matter, an equal speck of antimatter, born together in the same flash. The two are perfect opposites, created in identical amounts every single time. The math is strict. Matter and antimatter should always balance. Exactly, down to the last particle. Now here is the deadly part. When a piece of matter meets its antimatter twin, they do not bounce. They do not stick. They destroy each other completely, vanishing in a burst of pure energy. Total mutual annihilation. Nothing solid left behind, just a flash of light where two particles used to be. So follow the logic to its grim end. The Big Bang should have made matter and antimatter in perfectly equal amount. Then, as the young universe cooled and got crowded, every particle of matter should have run into a particle of antimatter and wiped it out. Every last one. The whole universe should have annihilated itself in its first moments, leaving behind nothing but a sea of light spreading through endless empty space. No galaxies, no suns, no Earth, no life. Just a cold, glowing void where a universe should have been. But look around. The matter clearly survived. Stars burn, oceans fill, your heart beats. The universe is overflowing with solid stuff that should have been destroyed at the dawn of time. Somehow, matter cheated death. It escaped the great annihilation and went on to build everything you have ever seen. That escape is the mystery. Scientists call it the matter-antimatter problem, and it is one of the deepest cracks in our understanding of reality. The rules say everything should have cancelled out. Reality says it did not. One of those two has to be incomplete, and so far the rules are losing. There is only one way out of this trap. The Big Bang could not have been perfectly balanced after all. Somewhere, somehow, matter must have been created in a tiny bit larger amount than antimatter. A microscopic surplus, a faint tilt in the scales. How tiny? Scientists believe that for every billion particles of antimatter, there were about 1,000,000,001 particles of matter. Nearly everything annihilated, 1,000,000,000 pairs wiping each other out in flashes of light. And from each round of destruction, just one lonely particle of matter survived. Those lonely survivors are everything. Every atom in your body, every star in the sky, is built from the rare leftovers of a war that nearly emptied the universe. You are made of the 1 in a billion that lived. But that raises a furious question. What gave matter the edge? What tilted the scales in its favor? And could CERN actually catch the universe cheating right now, in the act? To explain why you exist, scientists had to catch the universe playing favorites. And in 2025, the collider finally caught it red-handed. Remember the puzzle. The Big Bang should have made matter and antimatter in perfectly equal amounts, and they should have annihilated each other into nothing. For the universe to survive, something had to break the balance. Matter needed a secret edge over antimatter, even a microscopic one, to leave behind the leftovers that became everything. So, scientists went hunting for that edge. They asked a sharp question. Are matter and antimatter really perfect mirror images of each other? Or, when you look closely enough, does one of them behave just a little differently than the other? If the two were truly identical in every way, the universe would have cancelled itself out. So the survival of everything depends on a tiny flaw in the mirror. Physicists gave that flaw a name. They call it a symmetry violation, which is a fancy way of saying the mirror is slightly cracked, and matter and antimatter do not quite match. Scientists had spotted hints of this crack before, decades ago, but only in one narrow family of particles. They could never tell whether the same flaw showed up in the ordinary, everyday building blocks that make up protons and neutrons, the actual stuff of your body. And those building blocks are what really matter because they are what the universe is made of. So, the team running LHCb went searching. They studied a heavy, short-lived cousin of the particles inside you, a hefty blob built from 3 of the same basic ingredients found in every proton. They tracked how this particle fell apart. Then they tracked how its antimatter twin fell apart. If matter and antimatter were perfect mirrors, both should break down in exactly the same way, at exactly the same rate. They did not. The team sifted through years of crashes, comparing the particle against its antimatter twin over and over, and a gap appeared. The matter version and the antimatter version fell apart at slightly different rates. The mirror was cracked. For the first time ever, scientists watched this everyday class of matter and its antimatter opposite behave differently, with enough certainty to call it a real discovery. This was a genuine first. The crack in the mirror had finally been caught in the kind of particle that builds the visible universe, the family that includes the protons and neutrons in every atom of your body. It was the strongest sign yet that nature really does play favorites, tilting ever so slightly toward matter. And yet, even this victory carries a frustrating twist. Scientists measured the crack. They confirmed it is real. But when they checked how big it is, the crack turned out to be far too small to explain the whole survival of the universe. The tiny edge it gives matter is real, but it is nowhere near enough to account for the entire flood of stuff we see around us. So, the deepest part of the mystery still stands wide open. The universe clearly cheated death. Scientists have now caught it bending one rule, but the bend is too gentle to finish the job. Something bigger, something still hidden, must have given matter a far stronger push. That hunt leads straight to the strangest substance humans have ever made. A kind of stuff so dangerous and so rare that CERN builds it one fragile speck at a time. Somewhere inside that same giant ring, scientists make the most explosive substance in the universe, and a single touch sets it off. It is called antimatter, and you met its shadow earlier. For every kind of normal particle, there is an opposite version, a mirror twin with the reverse charge. The mirror twin of the electron is the positron. The mirror twin of the proton is the antiproton. On their own, these twins are perfectly stable and harmless. The danger only begins when they meet their normal partner. When matter and antimatter touch, they do not crash or crumble. They erase each other. Both particles vanish completely, and all of their mass turns instantly into pure energy. Nothing else in nature is this efficient. A stick of dynamite releases only a sliver of its hidden energy. Even a nuclear bomb converts just a tiny fraction of its material. But when antimatter meets matter, every last bit of both becomes raw energy, with nothing left over. Picture the math behind it. If you could somehow gather a single paperclip's worth of antimatter and let it meet a paperclip's worth of normal matter, the blast would rival a large nuclear weapon. That is from a speck you could rest on your fingertip. This is why antimatter shows up in so many science fiction stories as the ultimate fuel. The strange part is that the science is real. The energy truly is locked in there. So why are we not powering rockets and cities with it? Because making antimatter is staggeringly hard. and CERN can only produce it in unimaginably tiny amounts. We are talking about a few particles at a time, built one at a time, inside the most delicate machines ever designed. If you added up every scrap of antimatter humans have ever made, on purpose, across all of history, it would not be enough to power a single light bulb for more than a few minutes. There is a deeper reason antimatter is so precious. It barely exists. Look around the entire universe, scan every galaxy we can see, and it is built almost entirely from normal matter. The antimatter is gone, wiped out in that ancient war after the Big Bang. So if scientists want to study it, they cannot go find it. They have to build it from scratch, atom by atom, and building it is only half the battle. The moment you create antimatter, you face an impossible problem. It cannot touch anything. If a single antiproton brushes the wall of its container, or even a stray speck of air, it annihilates in a flash and is lost forever. Every surface in the world is made of matter, which means every surface is a trap waiting to destroy it. So imagine the challenge. You need to create the rarest, most explosive substance known, then hold onto it without ever letting it touch a single thing. No glass jar will work, no metal box, no container made of ordinary stuff could ever hold it, because the container itself would destroy the prize. Scientists had to invent something stranger, a way to grip antimatter using nothing solid at all, a bottle made of pure force, where the walls are invisible and nothing physical ever touches the substance inside. How do you trap something that destroys everything it brushes against? The answer is one of the cleverest tricks at CERN. To hold the unholdable, scientists build a bottle out of magnetism, with no walls, no lid, and nothing solid anywhere inside. This happens at a special part of CERN with a fittingly dramatic nickname. They call it the antimatter factory. Inside, scientists do something that sounds impossible. They take antiprotons, slow them down, cool them to a whisper above the coldest temperature in existence, and gently coax them into joining with positrons. When an antiproton and a positron link up, they form a single atom of antihydrogen, the antimatter twin of the simplest atom in nature. That antihydrogen atom is the prize. It is the rarest, most fragile thing in the lab, and the instant it forms, the clock starts ticking, because if it drifts even slightly and grazes a wall, it is gone in a burst of light. So how do you hold it? You use a magnetic trap, sometimes called a magnetic bottle. Picture a container with invisible walls woven entirely from magnetic force. The antihydrogen atom floats in the very center, suspended in empty space, never touching anything physical. The magnetic fields push gently from all sides, cradling the atom like an invisible hand holding a soap bubble without popping it. It is delicate beyond belief. The magnetic grip on these atoms is incredibly weak, so weak that the smallest disturbance can break it. A tiny jolt of heat, a faint vibration, a stray bump in the field. Any of these can knock the antihydrogen loose, and the moment it slips free and hits the wall, it annihilates. Holding it steady is like balancing a marble on top of a hill while the ground keeps trembling. For years, scientists could only trap these atoms for the briefest flicker before losing them. But they kept improving the magnets, the cooling, the timing. Eventually, they pulled off something remarkable. They held antihydrogen atoms steady inside the magnetic bottle for around 16 minutes. That may sound short, but in this world, 16 minutes with antimatter is an eternity. It gave scientists their first real chance to actually study the stuff instead of just glimpsing it. And studying it is the whole point. By holding antihydrogen still, scientists can finally compare it to ordinary hydrogen, side by side. If antimatter is a perfect mirror of matter, the two should look identical in every measurable way. The same light, the same behavior, the same response to the world around them. Any tiny difference, however small, could be a giant clue about why antimatter nearly all vanished and why you are here to wonder about it. So far, Every careful measurement has shown antihydrogen behaving exactly like normal hydrogen, almost frustratingly so. The mirror keeps looking perfect, even though the missing antimatter proves it cannot truly be. But there was one test scientists had dreamed about for decades, a question so basic that a child could ask it, yet so hard to answer that it took nearly 20 years to even attempt. If you took an atom of antimatter and simply let go of it, which way would it move? Would it fall down toward the floor, like everything you have ever dropped, or would it do something no normal matter has ever done, and fall up? For almost a century, nobody knew which way antimatter would fall, and the question was so wild it sounded like science fiction. Think about how strange this is. You have dropped 1,000 things in your life. A phone, a spoon, a ball. Every single one fell down, pulled by gravity toward the ground. It feels like the most obvious rule in the universe. Things fall. But antimatter is the perfect opposite of matter in so many ways. Its charge is flipped. Its very nature is reversed. So scientists had to ask an honest question. What if its gravity is flipped too? What if, when you let go of an antimatter atom, it floats upward instead of dropping? What if there is such a thing as anti-gravity, and antimatter is the key to it? This was a real scientific question, debated seriously for decades. If antimatter fell up, it would shatter our understanding of gravity and crack open one of the biggest theories in all of science. It might even hint at why antimatter is so scarce. Maybe it had drifted away, repelled by everything, escaping into the void. The idea was thrilling. It was also completely untested, because nobody had ever managed to drop antimatter and watch. The problem was always the same. To watch something fall under gravity, you need to hold it gently, then release it. And gravity is an extremely weak force. A magnet on your fridge easily beats the gravity of the entire planet pulling on a paperclip. So inside the magnetic bottle, the powerful magnetic forces totally drowned out the faint tug of gravity. Scientists could not see the gentle downward pull when the magnets were screaming over the top of it. The solution took patience and nerve. Scientists built a tall trap, stood it upright, and filled it with anti-hydrogen atoms held in the magnetic grip. Then they did the scary part. They slowly, carefully weakened the magnetic walls at the top and the bottom of the trap, easing off the force, bit by bit. As the magnetic grip faded, the only thing left to guide the atoms would be gravity itself. The question was simple. As the atoms slipped free, would more of them drift out the top or fall out the bottom? They ran the experiment, weakened the trap, and watched where the anti-hydrogen atoms ended up as they escaped and annihilated against the walls. About 8 out of every 10 atoms went down. The antimatter fell. It dropped toward the floor, the same direction your phone falls, the same direction everything has always fallen. There was no anti-gravity, no floating upward, no reversed pull. When you let go of antimatter, it obeys gravity just like the matter in your own body. This settled a question that had hung in the air for almost 100 years. Antimatter falls down. It closed one door on the mystery of the missing antimatter, ruling out the dream that it had simply floated away. Whatever erased nearly all the antimatter from the universe, it was not a strange reversed gravity. The puzzle of why matter won remains wide open, just with one wild idea crossed off the list. Now you might think antimatter only lives in this exotic lab, untouchable and far from your life. The truth is, this destructive mirror substance may have already saved someone you know. The most explosive substance in the universe sits inside hospital machines, quietly helping doctors look inside living bodies. This sounds impossible after everything you just learned. Antimatter annihilates on contact. It is rare, precious, and dangerous. So, how could it possibly be used in a hospital, near actual patients? The answer reveals just how clever humans have become at taming the impossible. The machine is called a positron emission tomography scanner, though almost everyone just calls it a PET scan. If you have ever known someone who needed doctors to hunt for a hidden problem deep inside the body, a tumor, a strange spot, something the outside cannot reveal, there is a good chance this machine was involved, and it runs on antimatter. Here is how it works, made simple. Doctors give the patient a tiny, harmless amount of a special substance that naturally releases positrons, the antimatter twin of the electron. The patient barely notices. Inside the body, those positrons travel a microscopic distance before they bump into ordinary electrons, the matter that every cell is built from. And you already know what happens when matter meets antimatter. They annihilate. Each tiny annihilation releases a precise burst of energy, two little flashes of light shooting out in exact opposite directions. The scanner is a ring built to catch those flashes. By recording where the light bursts come from, the machine maps out exactly where all those annihilations are happening inside the body. Cancer cells, for example, are hungry and active, so they soak up more of the substance and produce more flashes. They light up on the scan like glowing dots, revealing themselves even when they are buried deep where no eye could ever see. So the very same annihilation that makes antimatter the most dangerous fuel imaginable becomes a gentle searchlight inside a human body. The destruction is so tiny, so controlled, that it harms nothing, and instead saves lives by showing doctors precisely where to look. The patient feels nothing. The flashes are invisible. The machine simply reads the light and draws a map. It is a beautiful twist. The same physics that could level a city, scaled down to the level of single particles, becomes one of medicine's sharpest tools. Antimatter, the substance that nearly erased the universe, now helps catch diseases before they grow. Many of the techniques that made this possible trace right back to the kind of fundamental research done at places like CERN, where scientists chased pure curiosity and ended up handing the world a life-saving machine. This is the quiet secret of strange science. The research can sound useless, even crazy. Why study antimatter? Why smash particles for fun? Then years later, the wild experiment becomes the everyday tool that saves your grandmother. The collider may be hunting the deepest mysteries of reality, yet its discoveries keep leaking out into hospitals, computers, and technology you already use. So antimatter is real, it falls down, and it is already part of our world in ways most people never realize. Yet inside that penguin decay we started with, the troublemaker was not antimatter at all. It was a different particle, a heavier cousin of the electron, one that keeps showing up at the center of CERN's strangest puzzles. Scientists have a name for it, and a growing suspicion that it is hiding something. There is a particle raining down on your head right now, passing straight through your body, and it keeps acting like it knows a secret. It is called the muon, and you met it briefly inside the penguin decay. The muon is the electron's bigger cousin. In almost every way, it behaves like an ordinary electron, except it is roughly 200 times heavier. Picture an electron that hit the gym and bulked up massively. Same basic personality, far more weight behind it. Muons are everywhere, even though you never feel them. High above your head, particles from deep space constantly slam into the top of the atmosphere. Those crashes spray out showers of muons that rain down toward the ground at nearly the speed of light. Right now, several of them are passing through your body every second, slipping through your skin, your bones, and the floor beneath you without leaving a mark. They are like ghosts, here and gone before you could ever notice. The muon has one dramatic quirk. It does not last. A muon survives for only about 2 millionths of a second before it falls apart into lighter particles. Blink, and you have missed the lives of countless muons. That fleeting existence is exactly why scientists love studying them. They are born, they live their flash of a life, and they decay in a way the rulebook claims to predict perfectly. Here is where it gets interesting. Scientists have a deep belief about the electron and its heavier cousins. They believe these particles should be treated exactly the same by the laws of nature, identical in every way except for their weight. The fancy way to say this is that the different cousins should be perfectly balanced. An electron and a muon should behave like the same particle wearing different sized coats. But the muon keeps misbehaving. Over the years, The muon has shown up at the center of several of physics's biggest puzzles. Experiments keep finding tiny hints that the muon does not quite behave the way the rulebook demands. It wobbles where it should hold steady. It tilts where it should stay balanced. None of these hints alone has been strong enough to count as proof, and some have faded with more data. But the pattern is hard to ignore. Again and again, when something looks strange in the deepest experiments, the muon is somehow involved. And remember our penguin, when that B meson fell apart in its strange, rule-bending way, two of the particles it produced were muons. The very decay that started this whole mystery has the muon sitting right at its heart. So when scientists see that wobble, a quiet thought creeps in. What if the muon is the key? What if this heavy cousin feels a force the electron does not? A hidden push from some new particle that only it can sense? If that turned out to be true, it would crack the rulebook in a spectacular way. It would mean nature secretly plays favorites among these particle cousins, treating the muon differently for reasons no one understands yet. The missing pages of physics might be written in the muon's strange behavior. The muon raises wild possibilities. And wild possibilities are exactly why, when CERN's giant machine first switched on, a frightening rumor spread around the world. People genuinely feared the collider might swallow the entire planet. When the collider first roared to life, some people were convinced it would create a black hole and destroy the Earth. This actually happened. As the machine prepared to switch on, a wave of fear swept across the globe. Newspapers ran scary headlines. Worried people sent frantic messages. A few even tried to stop the experiment through the courts, filing real lawsuits to keep CERN from turning the machine on. Their fear sounded like the plot of a disaster movie. They believed that smashing particles together with so much energy might accidentally create a tiny black hole, a bottomless pit of gravity that would sink to the center of the Earth and slowly swallow the whole planet from the inside out. It is easy to see where the fear came from. The collider was the most powerful machine ever built. It crashed particles at energies never reached before. The word black hole is terrifying. Stitch those ideas together, and you get a nightmare, a science experiment that ends the world. So, scientists faced a serious job. They had to prove, clearly and calmly, that the machine was safe. And the way they did it is genuinely brilliant, because the answer was floating above everyone's heads the entire time. Remember those particles from deep space, the ones that rain muons down on you constantly? Many of them carry far more energy than anything the collider produces. These natural particles have been slamming into the Earth's atmosphere for billions of years, every single day, crashing with more force than the most powerful machine humans could ever build. The upper sky is hit by these violent natural collisions endlessly, all over the planet, non-stop, since long before life even existed. If those crashes could create a planet-eating black hole, it would have happened long ago, countless times over. Billions of years before anyone built a collider, the Earth is still here. The Sun is still here. Every star you see has been bombarded by these natural crashes for its entire life, and none of them have been swallowed. Nature has been running this exact experiment at higher energies forever, with zero disasters. That was the knockout argument. The collider does nothing that the universe has not already done 1 trillion times over, harmlessly all around us. And even in the wild case that the machine could create a microscopic black hole, scientists understood it would be so tiny and so unstable that it would evaporate instantly, vanishing in less than a flash before it could ever touch a single atom. The machine switched on. The Earth kept spinning. No black hole appeared. No planet got swallowed. The collider has now run for over 15 years, producing some of the greatest discoveries in science, and the apocalypse never came. The fear, while understandable, was based on a misunderstanding of how safe the experiment truly was. But that scare reveals something important about this machine. It pushes into territory so extreme that people genuinely wonder what monsters it might wake up. And while no black hole crawled out of the collider, the crashes really have produced things that, until recently, scientists were sure could not exist at all. Strange particles, impossible combinations, building blocks of matter glued together in ways the rulebook never expected to see. The collider keeps spitting out particles that, by all the old rules, were never supposed to exist. To understand why these are so shocking, you need to remember how matter is normally built. Quarks are the tiny building blocks locked inside protons and neutrons, and for a long time, scientists thought they only stuck together in two simple ways. Three quarks could clump together to make heavier particles like the proton, or a quark could pair up with an antiquark, its mirror twin, to make a lighter particle. Three together, or two as a pair. Those were the rules. Those were the only combinations anyone had ever seen. For decades, that simple picture held. Every particle scientists found fit neatly into one of those two patterns. The quark world seemed tidy and well behaved. Then the collider started finding things that broke the pattern. The team running LHCb, our penguin hunters, discovered particles made of 5 quarks stuck together. 5. Scientists call them pentaquarks, and they had been predicted as a long shot for years, but nobody had ever clearly seen one. Then, buried in the wreckage of countless crashes, there they were. Heavy, strange clumps of 5 quarks bound into a single particle, a combination the textbooks had treated as little more than a rumor. The discoveries kept coming. Scientists found particles made of 4 quarks, which they call tetraquarks. One of them was especially bizarre, a 4-quark particle that lived far longer than such a fragile thing had any right to, sticking around long enough for scientists to study it in real detail. They even spotted heavy new particles packed with rare ingredients, exotic blobs that had never been seen in nature before, born only for a flicker inside the violence of a collision. Each of these finds is like discovering a brand new way to build with the same old bricks. For ages, you thought the bricks only stacked 2 ways. Then suddenly you find towers built from 5 bricks, walls built from 4, shapes nobody knew were even allowed. The bricks were always capable of more. We just never had a machine powerful enough to force them into these strange new forms. These exotic particles do not break the rulebook the way the penguin might. They actually fit within the broad laws of physics, in corners scientists had simply never explored. But they prove something thrilling. The world of the very small is far richer and weirder than anyone imagined. There are forms of matter out there that flash into being for the tiniest instant, exist for less time than you could ever perceive, and then dissolve back into the wreckage. The collider is the only place on Earth where humans can glimpse them. And every one of these discoveries teaches scientists more about the strong force, the powerful glue that binds quarks together. The better they understand that glue, the better they can hunt for cracks elsewhere, including in our penguin. These exotic particles are like puzzle pieces, each one sharpening the picture of how matter truly works at the deepest level. Yet, even with all these discoveries, all these strange particles, and rare decays, scientists know they have only mapped a sliver of what exists, because most of the universe is not made of any of this. Most of the universe is made of something invisible, something the collider has been hunting for years and has never once managed to catch. Most of the universe is missing, and the collider has been hunting the invisible culprit for years without ever catching it. Here is the staggering fact. Everything you have ever seen, every star, every planet, every person, every particle in this entire video makes up only a small slice of what the universe is actually made of. All the normal matter we know about, the stuff in the rulebook, adds up to less than 1/5 of the total. The rest is a mystery so deep that scientists gave it a placeholder name because they truly do not know what it is. They call the biggest chunk dark matter. It is invisible. It gives off no light, no glow, nothing your eyes or any telescope could ever directly see. It is everywhere, woven through every galaxy, including our own, and yet it slips through normal matter like a phantom. Right now, Dark matter is very likely streaming straight through your body and the entire planet, leaving no trace at all. So if it is invisible and untouchable, how do scientists even know it is there? They know because of gravity. Dark matter has weight, and weight pulls. When scientists watch how galaxies spin, the numbers refuse to add up. Galaxies whirl so fast that they should fly apart, flinging their stars off into the void. But they hold together, as if some enormous, invisible weight is gripping them, holding the stars in place. That invisible grip is dark matter. We cannot see it, but we can feel its pull written across the whole sky. There is around 5 times more dark matter than all the normal matter in existence. Picture that. For every speck of stuff you can see and touch, there is roughly 5 times as much of something we cannot detect at all. The universe is mostly made of an ingredient that remains a complete mystery, and we are the tiny visible minority floating inside it. So, scientists turn to the collider, hoping to create dark matter and catch it in the act. The idea is bold. If dark matter is made of some unknown particle, maybe a violent enough crash could briefly conjure one into existence, the same way the collider conjures other rare particles. Then scientists could finally study the invisible thing that rules the cosmos. But catching it is fiendishly tricky, because dark matter would slip right through the detectors without leaving a mark. So scientists use a clever trick. They carefully add up all the energy before a crash, then add up all the energy in the spray of particles afterward. If some energy goes missing, vanishing into nothing the detectors can see, it could mean an invisible particle flew out carrying that energy away. A hole in the books, a ghost-shaped gap. For years, scientists have scoured the crashes, hunting for that telltale missing energy. And so far, they have found nothing. Crash after crash, the books balance. The invisible particle refuses to appear. Dark matter remains exactly as hidden as ever, mocking the most powerful machine humans have ever built. That silence is its own kind of clue, and it deepens the mystery rather than solving it. The biggest ingredient in the universe still hides just out of reach. Yet the collider did recently catch a different kind of ghost. A particle so slippery that, for decades, scientists thought a machine like this could never detect it at all. Trillions of ghost particles are blasting through your body every second, and the collider just caught some for the very first time. These ghosts are called neutrinos, and they may be the most elusive particles in all of nature. They are unimaginably tiny, carry no electric charge, and barely interact with anything at all. That last part is the key. A neutrino can fly through solid matter as if it were empty air. It can pass through a planet, straight through the rock and metal and molten core, and come out the other side without bumping into a single thing. The numbers are almost impossible to believe. Right now, every second, around 100 trillion neutrinos are streaming through your body. They pour out of the sun in unfathomable numbers and rain through you day and night, awake or asleep, indoors or out. You never feel a thing, because almost none of them ever touch you. A neutrino could travel through a wall of solid lead stretching for light years and still have a decent chance of coming out the far side untouched. This is what makes neutrinos so maddening to study. To detect a particle, you usually need it to hit something in your machine. But neutrinos almost never hit anything. They are the ultimate ghosts, slipping through every trap, ignoring every wall, flying past the most sensitive detectors as if they were not there. For a long time, scientists assumed the collider could never catch them. Yes, the crashes surely produced neutrinos, but those neutrinos would just zip away into the ground, undetected, lost forever. Then a small team had a clever idea. They built a special detector and placed it far down the line from one of the collision points, tucked into a tunnel, perfectly positioned to sit in the path of neutrinos streaming out of the crashes. They packed it with dense material, giving the ghostly neutrinos as many chances as possible to finally bump into something. Then they waited, hoping that out of the countless neutrinos pouring through, just a few would actually strike the detector and reveal themselves. It worked. For the first time ever, scientists detected neutrinos created inside a particle collider. The ghosts, born in the violence of the crashes, were caught in the act. It was a genuine first, opening a brand new window onto these slippery particles at energies never studied this way before. Why does this matter so much? Because neutrinos are deeply tied to some of the universe's biggest secrets, including that very mystery of why matter beat antimatter. Neutrinos are strange in their own right. They come in different types, and bizarrely, they can shift from one type to another as they travel, morphing in mid-flight like a shapeshifter. Some scientists suspect these shape-shifting ghosts could hold clues about the imbalance that let our universe survive. So, catching them at the collider is a big deal. It hands scientists a fresh tool to probe one of the most mysterious particles in existence, right alongside all the other hunts happening in the same machine. And all of these searches, the penguin, the dark matter, the ghost particles, the cracked mirror of antimatter, produce something almost as overwhelming as the physics itself, an ocean of data so vast that no single computer on Earth could ever hold it. The collider produces so much data that storing it would crush every laptop on the planet. So scientists built a brain that spans the globe. You already know the crashes come fast. Inside the machine, collisions happen around 40 million times every second, and each one sprays out a storm of particles that the detectors record in fine detail. If scientists tried to save every scrap of every crash, the flood of information would be so enormous that it would fill the world's hard drives in a heartbeat and keep going. There is simply no way to store it all. So the first thing the machine does is throw most of it away. Lightning-fast computers sit right beside the detectors and make brutal split-second choices, dumping the boring, ordinary crashes and keeping only the rare, interesting ones. They discard almost everything, holding on to just a tiny fraction that might contain something worth studying. Even after tossing out the vast majority, what remains is still staggering. The collider records a mountain of data every single year, far more than any one computer could ever process. Here is where the cleverness comes in. No single machine could crunch all of it, so scientists never tried to build one. Instead, they linked computers together across the entire planet into one gigantic shared brain. When a crash gets recorded at CERN, its data can be flung across the world in an instant, sent to powerful computer centers scattered across dozens of countries on multiple continents. Thousands of machines work on the problem at once, each handling a piece, all of them stitched together into a single worldwide web of computing power. Picture it like a colossal group project. One school could never finish the assignment alone, so the work gets split among thousands of schools around the globe, each tackling a small part, all reporting back to build the final answer. A scientist sitting in one country can tap into the combined strength of machines on the other side of the world, as if they were all in the same room. This planet-spanning network is one of the largest computing systems humans have ever assembled, built for the single purpose of understanding what happens when particles collide. And it has to be this big, because the discoveries are buried so deep. Remember our penguin? To find that wobble, scientists had to sift through around 650 billion particle decays, hunting for the tiny sprinkle of rare events that mattered. That kind of needle in a haystack search is only possible because of this global brain. Without it, the data would just pile up unread and unexplored, hiding its secrets forever. This is the hidden side of modern science that people rarely see. The big discovery makes the headlines: the strange particle, the cracked mirror, the rule-bending decay. But behind every one of those moments sits an invisible army of computers, quietly grinding through oceans of information, separating the rare signal from the endless noise. The physics is only half the battle. Taming the flood is the other half. So scientists have the machine, the detectors, and the global brain to read the results. They have already caught the penguin wobbling at 4 sigma. Now comes the part that will decide everything, because the most exciting fact in this entire story is not what scientists have already seen. It is what is coming next, sitting on the drives right now, waiting to be opened. The result that could break physics forever is already recorded, sitting in storage right now, waiting for scientists to finish reading it. This is the part that makes the penguin mystery so thrilling instead of frustrating. When scientists revealed that 4 sigma wobble, they were working from data gathered during an earlier stretch of the collider's life, a pile of crashes recorded over several years. That dataset was huge, hundreds of billions of decays, and it was enough to push the wobble to its strongest level ever. But it was not the whole story. Since then, the machine has kept running. It never stopped smashing protons, never stopped recording crashes, never stopped feeding its global brain. And in that time, scientists have already collected far more data on these exact penguin decays. We are talking about roughly 3 times as many of these B mesons as the study was originally based on, 3 times the evidence, already captured, already waiting. Sit with what that means. The single biggest hint of new physics in a generation was built on one batch of data, and a pile 3 times larger is already in hand, ready to be analyzed. Scientists do not have to build a new machine or wait years for fresh crashes to test their wobble. They simply have to dig through the mountain of data they have already gathered and see whether the penguin keeps misbehaving. This is the moment everything hinges on. Remember the 2 paths from earlier. If the wobble is just bad luck, more data should wash it away. The way the ghostly bump from years ago shrank and vanished once scientists looked closer. But if the wobble is real, if something new truly is tugging on these decays, then more data should make it grow. The gap should widen, the signal should climb, and if it climbs high enough, it could finally smash through that 5 sigma wall and turn a maybe into a discovery. So, scientists are racing through the new data, and the whole field is holding its breath. Every physicist who has watched this number flicker for over a decade knows that the answer is already sitting on the drives. The universe has already shown its hand. We just have to finish reading the cards. This is the strange agony of the situation. The truth exists. It is recorded. It is real. Somewhere in that ocean of new crashes, the penguin has either kept its strange behavior or fallen back in line, and nobody knows which yet. The result is fixed. Only our knowledge of it is missing. And the build does not stop there. The collider is about to get a massive upgrade, one that will pour out data at a rate that makes today's flood look like a trickle. Scientists are preparing for a version of the machine so powerful it will gather many times more crashes than everything collected so far, all aimed at questions exactly like our penguin. So the next few years are going to be some of the most important in the history of physics. The wobble will either rise into a discovery that rewrites the rulebook, or fade into a ghost that fooled everyone one more time. Either way, the answer is coming, and it is coming soon. To understand just how much is riding on it, you have to imagine what happens to all of science if that rulebook truly cracks. If the penguin wobble survives, and the rulebook finally breaks, it would be the biggest moment in physics in 50 years. Try to grasp the scale of it. The Standard Model has stood unbeaten for half a century. It has passed every direct test, predicted particle after particle, and survived every trap scientists could set. To find a real, confirmed crack in it would be like discovering that the most reliable map in the world had a whole continent missing, a place nobody knew existed, hiding in plain sight the entire time. A confirmed crack would mean one staggering thing. There is new physics out there, something beyond the rulebook, a new particle, a new force, a hidden layer of reality that scientists have long suspected but never proven. The missing pages everyone knows must exist would finally start to appear, and once you find the first crack, you know exactly where to start digging for the rest. The ripple effects would be enormous. Remember all the deep mysteries still unsolved. Why does the universe exist instead of nothing? What is the dark matter that makes up most of the cosmos? Why did matter beat antimatter? Why is gravity left out of the rulebook entirely? These questions have stumped the smartest people alive for decades. A genuine crack in the Standard Model could be the loose thread that begins to unravel them, because new physics in one place often points the way toward answers in others. Textbooks would be rewritten. The new particle or force would need a name, a place in the charts, a whole web of fresh experiments to study it. Scientists around the world would pivot their careers to chase it. Brand new machines might be designed specifically to hunt it down. A single confirmed wobble could redirect the entire field of physics for a generation, opening doors that have been locked since before you were born. And history shows how these moments unfold. When scientists discovered that invisible field giving particles their weight, it crowned 50 years of searching and earned the highest honors in science. When they first caught the mirror between matter and antimatter cracking, it reshaped how we think about why anything survived the Big Bang. Each of these breakthroughs started exactly where the penguin sits now, as a strange hint that refused to go away. There is a humbling flip side, and real scientists never forget it. The wobble might still vanish. More data could wash it out, just like the ghosts before it. The charming penguin, that fiendish calculation nobody can finish, might be hiding a bigger smudge than anyone expects, ready to swallow the whole mystery and leave the rulebook standing tall. If that happens, it would not be a failure. It would be science working exactly as it should, refusing to be fooled, demanding proof before belief. Either outcome teaches us something profound. If the wobble grows, we glimpse a deeper layer of reality for the first time. If it fades, we learn just how unbreakable the rulebook truly is, and how careful we must be when nature seems to wink at us. Both paths push human knowledge forward, but here is the part that should give you chills. Even the mighty collider has limits. There are questions it may never be able to answer, mysteries that lie just beyond its reach, and scientists already know it, which is why they are dreaming of something bigger, much bigger. Scientists are already planning a machine so enormous, it would make today's giant collider look small. Think about that for a moment. The current machine is one of the largest objects humans have ever built, a ring stretching about 17 miles beneath 2 countries, freezing cold and impossibly powerful. It found the famous weight-giving particle. It caught the cracked mirror of matter and antimatter. It spotted the penguin wobble that might rewrite everything. And yet scientists look at all of that and think, we need more. Why? Because the deepest questions demand even more power. To create heavier particles, to peer even further into the wreckage of a crash, to recreate moments even closer to the Big Bang, you need to smash particles harder than ever before. And to smash them harder, you need a bigger ring. A larger loop lets particles build up more speed and more energy before they collide, opening doors that the current machines simply cannot reach. So scientists have sketched out a dream machine, a future collider that would dwarf the one we have now. The proposed ring would stretch around 57 miles, more than 3 times the size of today's tunnel. Picture a circle so vast it would wrap around an entire region, buried deep underground. A loop so long it would take hours to walk. It would be the most ambitious science instrument ever attempted. A cathedral built to worship the smallest things in existence. A machine like that could chase the mysteries this video has been circling all along. It could hunt for the hidden particle tugging on our penguin, the one too heavy for the current collider to ever create directly. It could search harder for dark matter, that invisible majority haunting every galaxy. It could probe the cracked mirror of matter and antimatter with far greater precision, hunting for the deeper imbalance that let the universe survive. The questions that stump us today might finally meet a machine powerful enough to answer them. Of course, building such a thing would be a colossal undertaking. It would cost a fortune, take decades, and demand the cooperation of nations around the world. There are real debates about whether it is worth it, whether the money and effort might be better spent elsewhere. These are honest questions, and scientists argue about them openly. Pushing the boundary of human knowledge is never cheap and never simple. But the dream itself tells you something about people. We are not content to leave the deepest mysteries unsolved. We stand at the edge of what we know, stare into the dark, and start designing the tool that might let us see a little further. The current collider was once just a dream too, doubted and debated, and it went on to reshape our understanding of reality. The next machine could do the same, revealing wonders we cannot yet imagine. So, this is where we stand. A strange wobble in a one-in-a-million decay. Two machines pointing at the same crack. An ocean of fresh data already waiting to be read. A cracked mirror that explains why you exist. Ghost particles, invisible matter, and exotic forms of stuff that flicker in and out of being. And looming ahead, the dream of an even greater machine to chase whatever comes next. The most successful rulebook in history is trembling for the first time in 50 years, and whether it shatters or holds, the answer is already racing toward us, hidden in the wreckage of particles smashing together beneath a quiet field in Europe, waiting for us to finally understand what the universe has been trying to tell us all along.